Welcome to a Regents Physics Mechanics review. This is the multiple choice from the 2022 June exam. As you know, on the Regents Physics reference table, or if you're not familiar with that, on the reference table you have 5 main sections, 4 of them which have to do strictly with physics. You have mechanics, electricity, waves, and modern physics. What I'm planning to do with these set of videos and the review for this exam is to break up the 2022 June exam into these 4 subsections. So this first set of videos will be for mechanics. What I've done is gone in there, taken all the multiple choice out and all of the free responses out for the most part. Some were redundant, so they just did not come up again. But this will be the multiple choice from last year's exam. So let's get into our first example. All right, so a motorcyclist initially traveling east at 15 meters per second accelerates uniformly at a rate of 3 meters per second squared east to a velocity of 21 meters per second east. How far does the motorcyclist travel while accelerating? All right, so with any math question in Regents, you really just want to look at what they give you in the question, take it out of there, and then figure out what equation I'm going to end up using. So here, the first thing that I see, I have a motorcyclist initially traveling east at 15 meters per second. I see that I have some kind of motion, so that's how I know I'm in the mechanics portion of the reference table. And it's not going to be electricity, it's not going to be waves, it's most definitely not going to be modern physics. Obviously, the video tells you that, but that's how I'm going to figure out I go to that portion of the reference table based on this. So the first thing I have is that I'm traveling east at 15 meters per second. All right. You gotta know your units a little bit here. If you don't know that meters per second is for speed or velocity, the front page of the reference table actually has a couple of constants that have to do with speed or velocity. For the speed of sound of a wave, the speed of light as well, and it tells you that is meters per second. That's how I know I'm dealing with velocity here. So my initial velocity, it says initially, so I have here that VI is going to be equal to 15 meters per second, and it says it's to the east, so that's going to be a positive velocity. Then I'm told that I accelerate uniformly at a rate of 3 meters per second squared. So I have my acceleration there. It tells me it's acceleration. It also gives me the units for acceleration. Again, if you don't know the units for acceleration, they're on the front page of the reference table as well, with the acceleration due to gravity. So I have here an acceleration is equal to 3 meters per second. And again, that is also east, so that is going to be positive. Finally, I go to a velocity of 21 meters per second east. Again, it is going to be velocity. It tells me explicitly is velocity. That is my final velocity, and it is to the east again, so that means that it is positive. So I have here VF is equal to 21 meters per second. The last part here is going to tell me what I'm looking for. It says how far does the motorcyclist travel while accelerating. How far something goes, that is a distance or a displacement. So D is what I'm looking for here. All right, so now you go to your reference table, you go to mechanics, and you look for an equation involving all of these variables. If you're an AP and you're kind of like wondering what this is versus the AP reference table, it's the same idea here. Your initial velocity would just be V naught or Vx naught. Acceleration would be A subscript x. VF would be just Vx, and then D would be change in x. So very similar, same idea as the AP notations. So going to the reference table, I'm going to look for an equation with this, and it has no time. So the way I brought this up at the beginning of the year was calling it the timeless equation. That equation on the reference table involves VF squared equals VI squared plus 2AD. All right, so what I'm going to do with this to make my life easier, if this is like a part 2 and I had to substitute in with units, I'm going to do the algebra first, solve for D, then plug in, that will allow me to hopefully make the least amount of mistakes when doing the math here. So my ultimate goal here is to get d by itself. The first thing that I can see here is that whole 2ad term. Attached to that is vi squared. That's attached by a positive. So I'm going to subtract this from both sides. So we'll cancel out over here. Go to the other side, and I'll have vf squared minus vi squared. That is then equal to 2ad. My last portion here, I have displacement or distance that is attached to right now 2 times a. They're both being multiplied to d. Do the opposite of that and just divide out 2a from both sides of the equation. So then I have here that vf squared minus vi squared over 2 times my acceleration equals my displacement. So now I can just plug in what I have straight away. Don't need to do substitution with units on a part 1, but I'll just do it for practice purposes. So my final velocity is 21 meters per second raised to the second power minus my initial velocity, which is 15 meters per second raised to the second power, all over 2 times my acceleration, which is 3 meters per second squared. All right, so I'll pull this over to the side here just to do the math, but you can just plug into your calculator if you're good from here. So 21 raised to the second power, that's 441, so I'll put this all over here. So 441 meters squared second squared minus 15 raised to the second is 225 meters squared second squared, all over 2 times 3 is just 6 meters per second squared equals my displacement. 441 minus 225 gives me 216 meters squared second squared, all over 6 meters per second squared. That is equal to my displacement. Then do 216 over 6, and I'm going to end up with my displacement, or my distance traveled, being 36 meters. So that is answer choice 3. All right, so moving on to our next example. Example number 2. We have a 60 kilogram man is pushing a 30 kilogram lawnmower. Compared to the magnitude of the force exerted on the lawnmower by the man, the magnitude of the force exerted on the man by the lawnmower is. All right, so there's a lot of reading to go through here. For the most part, what you want to do is kind of take out, this has to do with forces, because it's saying a force here, the magnitude of the force. So going back to forces, we learned about Newton's 3 laws. So Newton's 3 laws are, the first law is inertia. A object at motion will stay at motion unless acted on by an outside force. Then you have Newton's second law, which is the sum of all forces, or the net force is equal to mass times acceleration, or it's written out on the reference table as A. Acceleration is equal to net force over mass. Or you have Newton's third law, which says every action has an equal and opposite reaction. This question is going over Newton's third law. Because you're pushing with a force on the lawnmower, that means the lawnmower is then going to push back with the same exact force. It doesn't matter what the mass of the man is versus the mass of the lawnmower. It's just that I push with some force. The force pushing back on me is going to be exactly the same. So this is going to be answer choice 3, the same force, and that is just Newton's third law. All right, so let's move on to our next example. All right, so number 3. We have a projectile is launched horizontally from a height of 65 meters with an initial horizontal speed of 35 meters per second. What's the projectile's horizontal speed after it's fallen 25 meters and then neglect friction? Alright, so this is one of those questions that's kind of meant to trick you because it's asking you to find the speed. They're really trying to trick you into calculating for the vertical velocity here, and kind of taking a lot of time to go through that. Usually you have enough time in the Regents anyways to go through all the questions, but this is just one of those things that if you don't have a good idea of projectiles going into it, this could be a question that can get you stuck up for a few minutes. You do a lot of math and then is actually then wrong. The main idea of this question is that we are launching the projectile horizontally. So that means whatever my initial horizontal speed is, that is the essentially x component, that speed is going to be the same throughout, because I'll do it as a subscript here. So my acceleration in the x direction is going to be 0 meters per second squared. We know my acceleration in the y direction is negative 9.81 for Regents, 9.8 for AP. If you're using that would also be fine. But I know that my acceleration in the x direction for a horizontal projectile is 0 meters per second squared. So that means if I have an initial horizontal speed of 35 meters per second, whatever it falls, that horizontal speed is still going to be the same. That's not changing at all. The only thing that would change here is my vertical speed, or my speed in the, vertical velocity, or vertical speed in the y direction, because you have that negative acceleration as it goes downwards. Since there is no acceleration in the x, my answer here is going to be 35 meters per second, because my initial speed was 35 meters per second, and I have no acceleration in the x direction, or the horizontal direction, as we know from earlier in the year. So answer choice 2, 35 meters per second. Alright, so number 4. We have an electric motor with a power rating of 6.48 times 10 to the 4th watts is used to raise an elevator weighing 2.8 times 10 to the 4th newtons at a constant speed. What is the total time required for the motor to raise the elevator a vertical distance of 20 meters? So again, another math question. So you're going to pick out what we have here within the question, and then we're going to go to the reference table and figure out which equation you're going to use. I have here, straight away I see power. There's two parts of the reference table. I have power, so my first thing, I have a power rating of 6.48 times 10 to the 4th watts. Again, if you forgot what the unit for power is, it gives it to you right here. Again, use the test to take the test is the best way to go about it. If you forget some units, they usually give it to you within the question in the first part. So if you forget it for, say, a part 2 free response question, you have it there in the multiple choice. So the first I see here is my power. That on the reference table is just P. So I can put here that P is equal to 6.48 times 10 to the 4th, and that is just W for watts. It says that we are raising an elevator weighing 2.8 times 10 to the 4th meters. So, newtons, sorry. 2.8 times 10 to the 4th newtons is my weight here. That is a force. So if you get that weight is a force, on the reference table you have Fg, F subscript g, that is my weight or force due to gravity. So in this situation, I do have the force, which is going to be Fg, and that is just 2.8 times 10 raised to the 4th, and newtons. Again, newtons is the unit for force. What is the total time required for the motor to raise the elevator a vertical distance of 20 meters? So I have a distance of 20 meters, and it's asking me to find the total time required. So I have here time is equal to my question mark. All right, so from here, I'm going to look on the reference table for an equation that involves Power, force, Fg. In this situation, it can just be force, so I'll put next to it just F. Force F, distance D, and time. So look towards the bottom of the reference table. I'll have the equation for power, and the equation for power is either work over time or work is Fd over time. So now, again, I want to just solve for t first and then plug in the numbers, because if I'm doing a part 2 and I'm going to plug in my units, it's just easier this way. I have to plug in the units over and over again. So I have here that power, since I have a force and a distance, I'll use this version of the equation over here. So I'm going to have power is equal to Fd times over t. All right, so I want to solve for t. So the ultimate goal is to get on one side of the equation by itself. Right now it is being divided by force times distance. So in order to get it now just on the top, the opposite of division is multiplication on both sides. So multiplying on both sides by time. On the right side it will cancel. On the left side I'll have power times time is equal to Fd. Last step here, I have power times time. I want to get time by itself. Just divide out the power from both sides of the equation because it's being multiplied to time. Cancel this out. I have then that my time is equal to Fd over the power. So now I can plug everything into the equation. Let me move it over a tiny little bit so I don't run out of room. So I'll start over here. So time is equal to, my force is the force due to gravity, or the weight of the elevator. That is going to be 2.8 times 10 to the 4th newtons. That is then multiplied by my distance that I raised the elevator. That is 20 meters. All over my power rating of the motor, which is going to be 6.48 times 10 to the 4th watts. Alright, so first thing I'm going to do here is just multiply these two together. If you're good otherwise, you can just do this in one step. But I'm going to have here 2.8 raised to times 10 to the 4th power. Times 20 is going to give me on top 560,000. Oops. And that is going to be just newtons times meters. All over my power rating, which is 6.48 times 10 raised to the 4th watts. That equals my time. Then when I just divide those two, so 560,000 divided by 6.48 times 10 to the 4th. When I plug this in to the calculator, I'm going to end up with an answer of 8.64. And that's going to be seconds. That's my unit for time here. Don't worry about like the newtons times meters over watts and making sure it ends up being seconds. It's a multiple choice question. This is a part 2 anyways. This would be more than enough work shown to get the full credit. And my answer then will be answer choice 3, 8.64 seconds. Let's move on to our next example. All right, so example number 5. The diagram below represents two forces, F1 and F2, acting concurrently on a block sliding on a horizontal frictionless surface. So which statement describes the motion of the block? All right, so in the front part of the question, or the beginning of the question here, it talks about the forces acting concurrently on the block. That just means the forces are acting at the same exact time. It tells me in the diagram based on the velocity vector that I'm moving to the right. That's just showing it has the V with the arrow below it. That's just showing that my block is moving in that direction essentially. So with this question, I have two forces. All I'm going to do with it is do Newton's second law, and then I can describe the motion based on that, whether I have any acceleration or I have no acceleration at all. Just look at all the example or all the answer choices down there. You have 2 with acceleration, you have 1 with constant speed, and then 4 is a way of talking about just acceleration, just in a different way. So let's see here, based on Newton's second law, what I'm going to end up with. So Newton's second law in the reference table is written out as A equals F net over M. What I'm just going to do is rearrange this real quick and write it out as F net equals MA. I'll take this one step further because Newton's second law, in better terms, is the sum of all forces on an object is equal to the mass times the acceleration. So the sum of all forces, or the F net in this situation, is just the vector sum of all the forces. So you have a force here, F1 is going to the right, F2 is going to the left. So that means, just based on sign conventions, the right is positive, the left is negative, so I'm going to add them up like that. So let me just show this. So the sum of all forces, that's the sigma F, is equal to mass times acceleration. So that just makes it a little bit clearer. All right, so the sum of all forces. The first force I have here is F1, that is to the right. That means that this force gets a positive sign because right goes with positive. So F1 is a positive force. F2 is to the left, and that is then a negative force because left, down, south, those are negative sign conventions, or west as well. So that means that my F2 is going to be a negative force. So that minus F2 equals the mass of the object times my acceleration. All right, so now we can just plug everything in that we have here. So we have F1 is 10 newtons, then minus the 10 newtons of F2 equal to mass times acceleration. So 10 minus 10, that gives me a 0 net force, or a 0 sum of all forces. So 0 newtons equals mass times acceleration. All right, so my block has to have some kind of mass. There's not going to really be a situation with this. It doesn't make any sense to do Newton's second law when you have no mass present. So the only thing that can give me 0 newtons here on the right side of the equation with MA would be 0 acceleration. So if I have 0 newtons on the left side, I must have 0 acceleration as well. So then what does that mean for a motion of the block? Answer choice 1 and 2 can go away right away, because this is talking explicitly about accelerating to the right or accelerating to the left. So these two answer choices are useless to me. Answer choice 3 is looking pretty good because it says we are moving to the right, which that is shown in the problem up here. The diagram shows that I have the velocity moving to the right, and then it talks about a constant speed. Constant speed means that my velocity or my speed is not changing. The thing that changes velocity or speed is acceleration, and in this situation we have 0 acceleration, so that means that I'm going to have a constant speed. So that's looking pretty good. And then 4, we have the block is moving to the left with decreasing speed. The first thing I see here that is wrong, it's not moving to the left. It tells me in the diagram that I'm moving to the right, so that's incorrect right away. And then with decreasing speed, it's just another way to say that it's accelerating in some way. So that answer is not correct. So answer choice 3 is the answer, both by just doing Newton's second law and by process of elimination based on doing the Newton's second law equation. So let's move on to our next example. All right, so example number 6. We have the magnitude of an unbalanced force applied to a 4 kilogram crate is 10 newtons. If the magnitude of this applied unbalanced force is doubled, the inertia of the crate is. Alright, so there's a lot of stuff here that you really don't need to worry about. Let's talk about unbalanced force. That just means we have a net force in some direction. It's saying that it's just 10 newtons, or the sum of all forces is 10 newtons. We have here the 4 kilogram crate. Inertia. What is inertia? Inertia just deals with how hard it is to move an object. So the greater the mass is, the harder it is to move. It doesn't say anything about my mass changing. So inertia is never going to change unless the mass changes. So that's what's driving inertia. I know there's a question with a table where it gives you a mass and a velocity, and it tries to trick you into thinking that has to do with like momentum, but you do that before you have that question like way before you deal with momentum at all. So the only thing that's going to make me have more inertia is a greater mass. So since the mass is not changing, the inertia is not going to change. So don't get tricked by forces or seeing a velocity next to it or anything like that. Inertia just has to do with the mass of the object. Since the mass is not changing, the inertia is not changing. So we have here answer choice 2, unchanged. So let's move on to our next example. Number 7, the elongation of a spring will be quadrupled if the magnitude of the force elongating the spring is. All right, so elongation, what does that really mean when it comes to a spring? That's just my displacement of the spring. So on the reference table, what's displacement? That is going to end up being just x. So that goes with an equation for a spring. And it says the force on the spring, that is going to be Fs on the reference table. Again, in mechanics, then what goes with that is my spring constant K. So let's look at this equation. This equation is Fs equals Kx. So really, it's just a like rule of ones, a law of ones question. I just plug in 1 for everything in the beginning, get like a base, what it's going to end up being, and then change whatever they're telling me to change to get a new force in this situation, because the force is going to be changing. So originally, with this equation, spin constant, we can make 1. The elongation or the displacement, we can also make 1, and that gives us 1 of the force on the spring. What I'm then changing is going to be the elongation of the spring. So x is going to end up being, so spring constant doesn't change, it doesn't say anything about that. And spring constant shouldn't change in the spring anyways, unless I'm changing the spring. What's going to change here is my displacement. That is going to be 4 times the original value. Just do 1 times 4. That gives me now 4 times the original force, which we can just call 1. So that means that if I quadruple the elongation of the spring, my force is going to quadruple as well, because there's no squared factor, there's no anything else. So this is a direct relationship. If that goes quadruples, then the force has to quadruple as well. So answer choice 4 is going to be the answer for this question. So let's move on to my next example. All right, so number 8. The diagram below represents a roller coaster car traveling counterclockwise in a vertical circle. So when the car is in the position shown, what are the directions of the centripetal force acting on the car and the velocity of the car? All right, so this is a circle. When it talks about centripetal force, it really means, for my AP students, we get into that a little bit more, the sum of all forces where that is pointing in a circle, and it's always going to be towards the center of a circle, especially for these types of situations. So wherever my centripetal force is going to be, that's the direction of the acceleration as well. We're not really worried about the acceleration though, but like think about like Newton's second law. Wherever the direction of my forces, or the sum of all forces, the net force, that's the direction of the acceleration of my object as well. In a circle, the sum of all forces is always going to be pointed to the center. That's where the net force is. So that's where my acceleration is as well. So if I'm looking for FC, it's essentially like this. And really for Regents, all you need to do is just know that centripetal force points towards the center of the circle. You don't have to make any crazy calculations in like vertical circles like this is. That's more of an AP idea. We just really deal with horizontal circles if it ever comes up. The other thing, my velocity. The velocity is always going to be tangential to the circle. So tangent just means a point and going straight off from that point. So based on where the car is, we're here, we go then straight downwards, and that's going to be my velocity. All right, so again for this, I'll need to recognize what type of force it is. I just need to recognize that the force is pointing towards the center, and the velocity will always be tangential to my direction of movement, because I'm going around the circle in the counterclockwise direction. That's why my velocity is going down at that point and not going upwards. So let's look at our answer choices and see which one is going to end up being. Answer choice 1 says that the centripetal force is directed to the right and the velocity is directed downward. Look, that's my answer. We just came up with that. So answer choice 1 is going to be the answer there. The rest of the answers, let's just go through them to explain why they would be incorrect. 2 says the centripetal force is directed downward. That is never going to be the case for our situations here. And it then says the velocity is directed to the right. That is just a mix-up. That is like a try to confuse you type of situation to kind of like mix up velocity and force. 3, centripetal force and velocity are both directed to the right. Again, that's just a mix-up of the velocity. It's not going to be directed to the right at that position, and they should never be in the same direction from what I can see. Yeah, they shouldn't be in the same direction ever. 4, same thing there, both directed downward. That would also be incorrect. At any point in the circle, the velocity is always tangential. The force is always going to be a sum of all forces, which is really what the centripetal force is. That net force is always going to be towards the center of the circle. So answer choice 1 is my answer. Force is to the right, velocity is downward. So let's move on to our next example. All right, so example number 9. The vector diagram below represents the path and distances run or ran by a student in a cross-country race. The displacement of the student from start to finish is. All right, so we just have to define what displacement is. And there's no equation for displacement given on the reference table, so it's just more of an idea known. Displacement is the change in position for someone or an object from my origin point to my finishing or final position. So it's that straight line change in position from start to finish. So essentially my displacement in this diagram is going to be from here, my start, to my finish, going straight downwards, and that's going to be in the south direction based on my compass over here. The main idea of this question is trying to trick you into calculating the distance ran, which would be adding up all these vectors here. So going to the right, 0.8 kilometers, going down, going back right or east 1 kilometer, going down south again, and coming back west. Really for this, you're just adding up the two southern vectors, the 0.8 kilometers and the 0.6 kilometers. Because again, it's just the change in position from my starting point to my finishing point, that straight line path. So following that straight line path, I have over here 0.8 kilometers south and 0.6 kilometers south. Those two are going to end up adding together, tip to tail if you even want to, and you're just going to add them, and then you have the direction is going to be south. So let's get rid of the answers that are not going to be useful to us in this situation right away. I can look at answer choice 1. That is not going to be correct because it involves north, so that is incorrect. Same thing with answer choice 3. We are going from north to south, not south to north. So it's going to be a southern displacement. And then just adding these up together, 0.8 kilometers plus 0.6 kilometers. That's going to give me 1.4 kilometers, and that is going to be in the southern direction based on my compass. If you want to just make sure to plug it into the calculator to get the 1.4, you can. You definitely don't need to for this situation though. So 1.4 kilometers south, that is answer choice 2, will be my answer. Let's move on to my next example. All right, so example number 10, we have a cannonball is fired with an initial velocity of 100 meters per second at an angle of 15 degrees above the horizontal. What are horizontal v subscript x and vertical v subscript y components of this velocity? All right, so going back to, this is projectile motion. Going back to projectile motion, we had the x and the y components. There are equations on the reference table that give you that a subscript x is equal to a cosine theta. And then you have a subscript y is equal to a sine theta. What I'm going to show you with this is where those actually come from, because it's not always that the x, or like the horizontal component, is going to be cosine. It's not always going to be that the vertical component is sine. So let's just show what we have here. My first thing I have here, I have an initial velocity of 100 meters per second at an angle of 15 degrees. Whenever I'm given some velocity at an angle, that means that that is essentially the resultant or the hypotenuse of my triangle, or the resultant vector of the two components of the velocity. So I just have here that VI is equal to 100 meters per second, and I have an angle theta which is equal to 15 degrees. All right, so like I was talking about, you have those two equations on the reference table. The a subscript x equals a cosine theta, and the a subscript y equals a sine theta. It is not always the case that x, or horizontal, is going to be cosine, and y, if you go deeper in physics, it will be for the most part in Regents. There's really not much of a difference. They just take that as face value and don't really worry too much about it. But if you're going to go further in physics at all, or you want to have a better understanding of where cosine actually comes from and where sine actually comes from, we're going to explain it right now. So we have here the 100 meters per second is essentially my hypotenuse of the triangle. So what I have here, I have 100 meters per second. With that, I have an angle theta. This then creates my two components, my Vy in this situation and my Vx. In a triangle, for this situation where the angle is, my Vx is the adjacent part of the triangle compared to the angle, and Vy is opposite. And 100 meters per second is my hypotenuse. All right, so let's start off first with my x component. Where does that actually come from? So in order to find my v subscript x, that is the adjacent to it. If I look for my trigonometry rules, those on the reference table as well, when I have an adjacent and I have the hypotenuse, the equation for that, or the trig function for that, is just cosine theta is equal to adjacent over hypotenuse. So then, if you want to solve for the adjacent value here, and I have the hypotenuse, I would multiply h on both sides of the equation, and I would end up with h cosine theta equals my adjacent value. In this situation, that's going to be my initial velocity, v, where vi is the hypotenuse, cosine theta equals v subscript x, which is the same thing as ax equals a cosine theta. So let me just do this as my hypotenuse is vi, which is the 100 meters per second. Cosine theta equals v subscript x. So that's where that equation actually comes from, is just finding the side of the triangle, essentially. So if you're a little bit confused with that, hopefully that explains it a little bit better. Same idea for sine. If I want to find the opposite here, which is going to be my v subscript y, doesn't mean v subscript y equals 0. I'm just showing that that's opposite. So let me actually write that out fully, so there's no confusion. Opposite for that one, and then adjacent for the other one. I don't need to write that fully out here. So we have opposite for v subscript y. If I plug this in now for my trigonometry, finding the opposite is going to be sine when I have the hypotenuse. So sine theta equals opposite over hypotenuse. Same idea, multiply hypotenuse on both sides because it is being divided by the opposite. When I then end up doing that, so I have hypotenuse sine theta equals the opposite there. Then if I plug in what I have here, h, again, the hypotenuse is my vi sine theta equals my v subscript y. So that's how you get it based on the trigonometry there. It just comes straight from finding a side of the triangle. That's where those equations come from. A subscript y equals a sine theta, or a subscript x equals a cosine theta. Again, if you go further into stuff, that's not going to be the same all the time. It's just based on where that angle is. But in Regents, they don't do anything besides the angle being with the horizontal. So you don't have to really worry about that. So let's just plug everything in. So for my v subscript x, if I plug this in as now 100 meters per second, that's my initial velocity. Cosine of 15 degrees equals v subscript x. Now just plug everything in. So make sure your calculator is in degree mode. 100 cosine 15 is going to be 96.6 for v subscript x. That's meters per second is Vx. Then the same thing for the y direction, 100 meters per second. Sine 15 degrees equals Vy. Plug that into your calculator, same idea. 100 sine 15 is 25.9 meters per second. Equals Vy. So look for the answer that involves both of these here. So what I have here, I have answer choice 1 is going to be my answer. That shows that v subscript x is 96.6 meters per second. V subscript y is 25.9 meters per second. And there's actually no other answer choices with the v subscript x being the correct answer. So you can get rid of the rest of them right away. So answer choice 1, you don't even have to even do v subscript y to get the answer here. Answer choice 1, 96.6 meters per second for my horizontal, 25.9 meters per second for my vertical. So let's move into our next example. Example number 11 here, we have a 1200 kilogram car is moving at 10 meters per second when a braking force of 3,000 newtons is then applied. How much time is required to bring the car to rest? So again, a math question, we're going to pick out what we have in the question, then go to the reference table and figure out which equation we can use. So the first thing I see here is a 1200 kilogram car. That is a mass. So mass is 1200 kg. It is moving with an initial velocity of 10 meters per second. Because later it says I'm bringing it to rest, so I can put here as Vi is equal to 10 meters per second. Or a braking force here of 3,000 newtons. So I have a force of, it's going against me because I'm slowing down, so I can make it negative. So negative 3,000 newtons. It's saying how much time is required, so that is t. It's asking me to find that, says my question mark, to bring the car to rest. So Vf is going to be 0 meters per second. All right, so I have a mass, I have two velocities, I have a force, and I'm trying to find time. So there's two things with this that I can kind of look at the reference table for. On the reference table, there's only one equation that involves force and time, and that is the impulse equation. So we should be working with that because we have mass and velocity as well, and you know that momentum is mass times velocity. And I have force and time, and that's impulse. When I have a force at a time, I can figure out what the impulse is based on that, as well as just the change in velocity of the object. I can figure out the change in momentum or the impulse. That equation on the reference table is this: J equals the change in P, which is then equal to F net times T. I'll just write F for the situation times T. All right, so change in momentum. Momentum, again, is mass times velocity. Doesn't say anything about my mass changing, so the only thing I can change here is velocity. So going one step further here, J is equal to the mass times the change in velocity, which is then equal to the force times time. Alright, so what I have here, I can really just set these two parts of the equation equal to each other, because I don't really need to find the impulse with one and then go and you plug it back into the equation. I can just set m times the change in v is then equal to the force times time. So what I'm going to have here, change in v, again, I'm just going to solve for t right now and then plug in the numbers. So mass, change in velocity, a change in anything is always final minus initial. So what I have here is Vf minus Vi is equal to force times time. I want to get time by itself. It's being currently multiplied to force. So just divide out force from both sides of the equation. And we should end up with here that my mass times Vf minus Vi over the force applied is equal to the time it takes for me to come to rest. All right, so now I can plug in everything that I have here and can figure out the time. My mass here is 1,200 kilograms, so we'll start over here. So 1,200 kg times my final velocity, that is 0 meters per second. Oh, oops. Minus my initial velocity, that is 10 meters per second, all over the force, which is negative 3,000 newtons. And you're going to see why I did negative in a second, because then I had to end up with a positive time. So really what I have here is just 1,200 times negative 10, because 0 is 0, so you can really not really worry too much about this. So 1,200 times negative 10 here. When I plug this into the calculator, I'm going to end up with negative 12,000. So I should end up here with negative 12,000 kilograms times meters per second. Over negative 3,000 newtons is equal to time. I have a negative over a negative, so I just divide those two numbers. And I'm going to end up with an answer of 4 seconds. So time is equal to 4 seconds. That is going to be answer choice 4, 4.0 seconds. Let's move on to our next example. So example number 12, a student uses a strain to whirl a 0.25 kilogram mass in a horizontal circular path that has a 0.8 meter radius. If the magnitude of the centripetal force exerted on the mass with the strain is 25 newtons, the speed of the mass is. All right, so what I'm given here first is a mass. So I have a 0.25 kilogram mass. So I have mass here is equal to 0.25 kg. It says that I'm in a circular path, so that's my first tip-off that I'm dealing with centripetal acceleration or centripetal force, but then it will explicitly tell me this later. It says that the circular path has a radius of 0.8 meters. The magnitude of the centripetal force exerted on the mass by the strain is 25 newtons, so that means I have Fc. And it tells me this is 25 newtons. I'm trying to find the speed of the mass, which is v. So that's my question mark. All right, so there are two equations on the reference table that deal with centripetal force or circular motion. These two equations are Fc equals mac, and it tells you what AC actually is. So Fc equals mac, which I'll start off with here. Again, if you don't know what centripetal force is on the reference table, look on the right side, look for centripetal force, Fc. There's only one equation that involves it. it's FC equals MAC. This is not one that is present on the AP reference table. It is present on the Regents reference table. Because really the idea behind this equation is it's just Newton's second law in a circle, and they write it out as the force is equal to MA, unlike how regular Newton's second law is just written out as A equals the force over the mass. This one here is the force equals MA, which is the normal way to write out Newton's second law. So again, this is Newton's second law for circles. FC equals MAC. What is AC? That is also on the reference table. So look for centripetal acceleration. That is going to be on the reference table as V squared over R. Let me fix the 2 there. All right, so now I have everything that they gave me in the question. Now it's all in my equation. I can solve for V and then plug in my numbers. This one's a little bit of a trickier one because you have a squared value there, so you get the square root at one point to get V by itself, and it's being both multiplied by a value and divided by a value. So the first thing I'm going to do here is see that V squared over R is being multiplied by M. That means to move it over to the other side because I want V by itself is just divide out M from both sides. So dividing this out, cancel this out. I have the centripetal force is equal over the mass is then equal to V squared over R. Again, I want V by itself. Now is being divided by the radius R. So the opposite of that is multiplying R on both sides of the equation. So this will cancel out on the right side. On the left side, you have the centripetal force times my radius R all over the mass equals V squared. The last thing here to get V by itself is currently being squared. So do the opposite of squaring something, that is taking the square root from both sides of the equation. And I will end up with the square root of the centripetal force times the radius over the mass. Let me make that a little bit clearer. That's square root in the entire thing. Square root of the centripetal force times the radius over the mass is equal to my velocity. So now we can plug everything in. Again here, square root of all of this. Centripetal force is going to be 25 newtons. That is multiplied then by my radius, 0.8 meters, all over my mass in the situation, which is 0.25 kg. That is then equal to the velocity v. So then going the step in between here, 25 times 0.8 is going to be 20. And that is just newtons times meters all over 0.25 kg equals my velocity. Do 20 divided by 0.25. You're going to end up with 80. So the square root of 80. And this should end up being, because we have meters per second at the end, just meters squared, second squared. But again, doing all the units is not as important here. It's just good practice for the Regents. You don't have to do this on the day of the Regents. If you understand the question, just go through and do it as quickly as possible. Obviously, do it correct, but like you don't have to go through all of these steps to get the right answer. If you can figure it out just by doing it in your calculator, that's fine as well. Especially for the part 1s, not the part 2s. You have to show all the work. Do the square root here of 80. 8.9 is going to be my answer. So 8.9 meters per second equals my velocity. That is or speed. That is going to be answer choice 2 here. Let's move on to our next example. All right, so example 13. Which graph best represents the motion of an object traveling at a constant positive velocity? All right, so we have a displacement versus time graph. how would I get a velocity from displacement versus time? So let's look at the reference table. If you have no idea how to do this. Displacement versus time is the lowest version essentially of all of the motion graphs. It goes from displacement versus time to velocity versus time to acceleration versus time. So for people who are taking pre-calculus right now, I know you guys have went over derivatives and things like that, so you should have a better idea of the motion graphs now than you did at the beginning of the year. So for this, essentially, if you have that idea, the derivative of displacement versus time, or a displacement function with respect to time, is going to be velocity. In better terms, or in easier terms, that just means that the slope of the graph is going to be, I get my velocity based on that. And that really just comes from what is slope. Slope is the change in y over the change in x. If you look at the graph here, the y is going to be the change in my displacement. The x is going to be the change in my time. If you look at the reference table, the equation for average velocity is just d over t, so that is going to be equal to my velocity. The y again is displacement, the x is time, so that's how I'm getting my velocity from that. The other thing here, I want a positive velocity, so I want a positive slope. So if I look at two of my answers already, those can go away. 2 and 4 are both negative velocities because they both have negative slopes, so both of these are incorrect. And if I want a constant positive velocity, that means that I want my slope to be the same the entire time. I do not want it to change. Between these two answers that are left, 1 and 3, only answer choice 1 has a constant slope. So that means I'm going to end up having a constant velocity. So answer choice 1 is going to be my answer. Answer choice 3 would show that there is some acceleration. So I'd have a change in velocity. I would have an acceleration versus time graph that would have a positive acceleration. 2 again, that is showing a negative velocity, and then 4 is showing a change in velocity again, but also a negative slope. So let's move on to our next example. All right, so example number 14. You have a gravitational force of magnitude F exists between Earth and a satellite on Earth's surface. The satellite is sent into orbit at a distance of 3 Earth radii above the Earth's surface, as shown in the diagram below. What is the magnitude of the gravitational force between Earth and the satellite when the satellite is in orbit? Alright, so this is a law of one situation again. This is pretty much, again, from last year's Regents. This is pretty much the only time you're going to see the universal gravitation equation show up. Sometimes you might have a proper calculation, but for the most part, they like to do the just like change in distance one, especially with this. Distance is a squared factor on the bottom of the equation for universal gravitation. So they like to test your ability to be able to like manipulate that equation essentially. So again, how did I figure out it was universal gravitation? What I have here, it's saying I have a gravitational force. There are two different equations for gravitational force on the reference table. So I'll just write them as Fg equals, even though they're not both Fg equals. So you have the one for weight, which is Fg equals mass times the acceleration due to gravity, or G equals Fg over m. Or you have universal gravitation, which is Fg equals G m1 m2 all over r squared. Between these two, the one that makes the most sense again when dealing with this question is going to be the universal gravitation formula, Fg equals Gm1 m2 all over r squared, because I'm dealing with a gravitational force and I'm dealing with distance involved with that. Fg equals mg is really not going to be helpful beyond, at least for Regents, beyond just finding the weight of an object or doing some kind of Newton's second law calculation. So we have here Fg equals Gm1 m2 all over r squared. Again, this is a law of one situation. So for my first scenario where I'm just on Earth, I'm 1 Earth radius away. So I'm going to plug in here to my equation G here is always going to be 1 when I do law of lunge because it is a constant. The mass of the satellite and the mass of Earth, it doesn't say anything about either of those changing, so I plug in 1 for both my masses. And my original distance from the center of the Earth, which is where we are always going to take these calculations, the center of the object, or the center of the planet, is going to be just 1 Earth radii. So we have here 1 squared on the bottom. That's where we get our force F here. So that is the 1F that they give to us in the problem. Now I can go one step further and figure out what is going to be my new force when I get into orbit. So again, the top is going to stay the same because it doesn't say anything about the mass of my satellite changing. It doesn't say anything about the mass of Earth changing, obviously. So I'm just going to plug in again 1 times 1 times 1 on top. And then on the bottom, do I plug in 3 or do I plug in 4? What am I going to plug in here? I have 1 Earth radius away initially. I then add 3r to it. That means I'm actually going to have 4 times my original distance, not 3 times my original distance. So I'm going to plug in here 4 squared. That means that on the bottom here, 1 times 1 times 1 on top is just 1. 4 squared is going to be 16. So that gives me 1/16 the original force. So that means I'm going to have answer choice 1/16 of F. And again, the tricky thing with this one is just using the squared on the bottom. The other tricky thing here is figuring out whether I'm going to plug in 3 or I'm going to plug in 4. The reason why I plug in 4, I'm always going to be 1 Earth radius away if I'm on the surface. So initially I'm 1 Earth radius. Then I add 3 of those to it, so I'm 4 away from the center of the Earth, not 3. So that's why it's 4 squared on the bottom, not 3 squared, which gives me the 1/16. The 4 squared obviously is 16, so 1/16 of the original force is my answer. So answer choice 1 is the answer. So let's move on to our next example. As example number 15, the graph below represents the motion of an airplane that starts from rest and takes off from a straight runway. So this is a velocity versus time graph. It's asking me which quantity is represented by the slope of the graph. So that means, like, is it acceleration? Is it displacement? Is it average speed for this situation they're giving us as an answer choice, or total distance traveled? So again, when it says slope, we know that that is change in y over change in x. For my pre-calculus people, again, this is really, you've maybe done a little bit of this with derivatives. If you started with that already, you can figure out what the derivative of velocity is with respect to time. So with this though, that is just the slope in like algebraic terms. So the slope here, change in y over change in x. My y-axis is giving me velocity, so that is change in velocity over change in time. V over t, if you look at the reference table, V over t is acceleration. The change in velocity over change in time is my acceleration. So the slope of a velocity versus time graph, or the derivative of velocity with respect to time, is my acceleration. That is going to be answer choice 4. All right, so let's move into our last example. All right, so example number 16. We have the diagram below represents 2 horizontal platforms that are at different heights above level ground. A ball rolls off the taller platform with a horizontal speed of 15 meters per second and travels through the air, landing on top of the shorter platform. What is the total time the ball is in the air, and neglect friction? All right, so this is going to be a horizontal projectile question. What I've done here is add in my little table for this, showing the x and y components that are horizontal and vertical components of this, and then my displacement, my initial velocity, my final velocity, my acceleration, and my time. All right, so if you don't need to do this for the question like this, or any question like this, if you have a greater understanding of it and you don't want to write this whole table, You don't have to. Just organizes your thoughts a little bit better, just like a verb chart for circuits. So let's just write out what we have here first. The first set tells me within the question I have a horizontal speed of 15 meters per second. So that means that is going to be my initial velocity in the x direction. That is 15 meters per second. What other things do I know about the horizontal direction here? I know that in the horizontal direction, my acceleration is 0 meters per second squared. I have no change in my velocity. So that also then means that my final velocity is also 15 meters per second. That's all I have so far in the x direction. I do not have the horizontal distance it travels. The other things that I have here, y direction. First thing that I can see in the y direction, or first thing I should know about the y direction, my initial velocity. If it's a horizontal projectile, I'm going to have 0 meters per second for my initial velocity. Essentially, this is treated as a dropped free fall problem. So if I'm dropping an object, I have 0 meters per second as my initial velocity. My acceleration in the y direction is negative 9.81 meters per second squared. I do not have my time yet. Time is the same for both the x and the y, but I can find my displacement. This is a little bit of a tricky question because usually in a Regents situation, they'll just give you that it drops from 6 meters and it falls to the ground. This one, though, they started you off at 6 meters above the ground and then went to 3.6 meters above the ground. So I must subtract these two. Remember, final minus initial is going to be the change in a position or change or my displacement. So I gotta do 3.6 minus 6.0, and I will end up with my displacement because I'm going downwards. I should have a negative displacement. So 3.6 minus 6.0 is going to give me negative 2.4 for my displacement. That is in the y direction. So negative 2.4 meters for that. So between my components, I'm trying to find time, and that's the same between both, so I can use either the x or the y if I have enough in either of them based on the kinematic equations to find my time. So let's see in the x direction. In the x direction, I have initial velocity, I have final velocity as well, and I have acceleration. The problem with this one is that my initial and my final velocity are the same thing, so I cannot use the final velocity equation, the Vf equals Vi plus At, to find my time because it will lead me to nothing. I do not have enough for any of the other equations. Again, the timeless equation will lead me to nothing because my acceleration is 0, and the displacement equation, d equals Vit plus 1 half At squared, is also not going to lead me anywhere because I do not have displacement. So I'd be missing two things and not just one. In the y direction, I have displacement, I have initial velocity, I have acceleration, and I'm trying to find time. If I look on the reference table, I do have an equation that involves all of this, and it is going to be d equals Vit plus 1 half At squared. So again, what I'm going to do with this is solve for t by itself there and then plug in my numbers. So let's start off with this. So first thing I know here is that my initial velocity is 0. That's being multiplied by time, so this is going to go away. So I'm really now left with d equals 1 half At squared. So the first thing I want to do here is I want to get t by itself. So I see that as being currently multiplied by 1 half a. So what I can do with this is divide out 1 half a from both sides of the equation. And then from that, d over a is simple. D over 1 half, do the opposite of that now, essentially multiplied by 2. So I have here on this side 2d times my acceleration equals t squared. So now, last thing here, I want to get t by itself on the right side is currently a squared value. So do the opposite of that and take the square root of both sides of the equation. And I end up with the square root of 2 times my displacement over my acceleration is equal to time. So now I can just plug this into the equation and end up with my answer here. So the square root here, I'll move it up here, I guess. The square root of 2 times my displacement, which is negative 2.4 meters, all over, make the square root bigger so it encompasses everything, all over my acceleration, which is negative 9.81 meters per second squared, equals my time. So if I'm plugging this all in now, 2 times negative 2.4, that's going to give me here negative 4.8. It's negative 4.8 over negative 9.81 meters per second squared. Equals my time. Do those two, 4.8 divided by 9.81. That's going to end up as 0.489. That's what I'll write out as. So the square root of 0.489, and that will end up being seconds squared. My meters cancel out. My seconds squared comes to the top, is equal to my time. So then take the square root of 0.489 in your calculator, and you should end up with 0.699, which is 0.7 seconds, equals my time. So that is my answer. Answer choice 3, 0.7 seconds, and you could put that into the table here for both them, though you're not going any further with this, so you don't need to. So my answer choice here, answer choice 3, 0.7 seconds. So I hope this review was helpful. I will get up the free response from this exam as well. And then we will also go through electricity, waves, and modern physics. All right, see you guys in class.